Hello again, I'm Amashni. In this lesson, we will focus on the properties or characteristics of the equilateral triangle. You should remember from lesson 2 that an equilateral triangle has 3 sides of equal length. By the end of this lesson, you should be able to list the characteristics of equilateral triangles. Do you still remember the tools that we can use to analyze space? They are defining, constructing, and transforming. We'll begin this lesson by constructing our equilateral triangle and then cut it out to use as a model later on. So try this fun exercise with me. To begin, we start labeling our rectangle. We'll call this point A, point B, C, and D. The next thing is to fold AD onto BC to create a lengthwise fold line. So we fold AD onto BC. Make sure that your ends meet and fold the page. Now open up the page and you see our fold line here. I will mark the fold line as EF. Now we take point A and try to fold onto line EF. We fold in such a way that we create a line that passes through point B. So keep pulling point A onto our fold line and watch so that we can create a line that passes through point B. So if I fold on this, we see that this line that we've just folded passes through point B. I mark the point at the top here as G. I mark the point where point A touches the fold line as R. And we then open up the page. Now, we construct a line through point G and R to the bottom of the page. There we go. And I will just draw in another line here so we can see our triangle better. And there we go. So this is now our equilateral triangle, BGR. And let's just label this point here as H. All that's for us to do is to cut out our triangle BGH. As soon as you have cut out your triangle, you have to measure the lengths of the sides to confirm that it is indeed an equilateral triangle. So, in other words, we have constructed a model of the equilateral triangle. As before, the first thing we will try to do is to find all the possible lines of symmetry in the equilateral triangle. Do you remember what the line of symmetry is? Symmetry. The symmetry line divides a shape into equal parts. Let's see what we mean by this. So let's fold GB onto GH. So, folding. And there we have. So we see that our angle GBH fits directly onto GHB. Do you think we can find more lines of symmetry in the equilateral triangle? Let's have a look. So did you see that the equilateral triangle has 3 lines of symmetry? I have drawn in all the lines of symmetry. Let's now take our ruler and measure the length. Okay, and we see that we get 30 centimeters. So we have GK is equal to 30 centimeters. Let's measure the other two lines of symmetry. Right, let's now fill in all the angles that we know are equal. Remember, when we folded, we found that these two angles fit directly onto one another. Let's mark them with the same symbol to show that they are equal. Now remember, when we folded, we found that this side also fits directly onto this side. So we can say that GM is equal in length to MH. Right. We also know that when we fold it along GK, that side BK fits directly onto KH. Mark this off with the same notation as well. And our last line, when we fold it this way, we know that GI is the same in length as BI. Now there's another interesting thing that we can observe. Look at these symmetry lines again. Do you see that the symmetry lines intersect at this point? We will call this point O. The point O is the point of intersection, but it is also called the point of concurrency. Do you remember what concurrency means? Concurrency. The point of concurrency is where two or more line segments, rays, and even planes intersect in a single point. Now I want to have a look at the relationship between the lines of symmetry and the angles at the vertex in an equilateral triangle. Let's go back to our model. Do you remember that our line of symmetry has bisected the angle at the vertex and passed through the midpoint of line BH? And this is the same for all the lines of symmetry. They have bisected the angles at the vertex and passed through the midpoint of the opposite side. In our equilateral triangle, the symmetry lines can also be called medians and angle bisectors. Do you remember these terms from lesson 2? A line segment from a vertex to the midpoint of the opposite side is called a median. A line that bisects an angle is called the angle bisector. For our next activity, I will use a set square to measure the angle that the line of symmetry makes with the opposite side. So take our set square and measure the angles. Now if you look carefully, you see that the angle at M is indeed a 90-degree angle. So let's just mark that in. Let's measure the other angles. GK is the line of symmetry, and we see again that this is a 90-degree angle. Mark it in. And lastly, at I, we see that this angle at I is also 90 degrees. So we can say in our equilateral triangle, the lines of symmetry bisect the opposite sides perpendicularly or at a 90-degree angle. This property or characteristic brings us to two more important terms that you should remember from lesson 2. A line segment from the vertex of a triangle that intersects the opposite side perpendicularly is called an altitude. Perpendicular bisector is a line that bisects a line segment at a 90-degree angle. So we see that in our equilateral triangle, the lines of symmetry can also be called altitudes and perpendicular bisectors. Now there is another special relationship that we find with these lines of symmetry. Let's go back to our model and see. We have already established that these lines of symmetry are of equal length. Remember, we measured them to be 30 centimeters each. Do you also see that these symmetry lines divide each other into two segments? If we look at the line segment HI, we see that it is divided into HO and OI. Now, do you also notice that HO is larger than OI? Do you think that there might be a relationship between the long and the shorter sides? Let's measure with our ruler and find out. HO measures 20 centimeters. HO 20 centimeters. Let's measure OI. OI is 10. So writing this relationship, so we see OI is 10 centimeters. So if we write this relationship, we see it is in the relationship 2:1. So we can write this ratio or relationship in a formula. HO equals 2 times OI. So this means that 2 lengths of OI is the same as 1 length of HO. Now let's use a pair of dividers to see whether this relationship exists for the other 2 lines of symmetry. So place our divider points onto our shorter line segment KO, and we see that GO is 1, 2, the lengths of KO. And similarly, if we place our divider points onto OM, we see that OM is half of BO. Now that we've done all the hard work, let's have some fun. For this next activity, we will use transformation to better understand this shape. Have a look. Now, apart from the large triangle, do you see any other triangles? You should be able to notice that there are 6 smaller triangles. Can you perhaps see what kind of triangles they are? Now, if you were to cut out any one of these 6 triangles, and I have already cut out mine, you should see that they all fit directly onto one another. And if I flip the triangle, keep flipping, and lastly, let's have another look at our big triangle to see if we can find any other triangles. Can you see that the lines of symmetry also form 6 larger triangles? Once again, I have a cutout of our triangle. We will use transformation to see that these triangles do indeed fit onto one another. And if we flip the triangle, we see, yes, that they are directly fitting onto each other. And lastly, do you see that all our triangles are right-angled triangles? Do you think there is a possible relationship between the small and larger triangles? Let's have a look. So let's take our cutout of the smaller triangle and place it onto our larger triangle. It seems as if they have the same shape but different sizes. This type of relationship is called similarity, and we will take a closer look at this relationship in a later lesson in the series. Isn't it fascinating what we can find when we look at shapes a little more closely? Let's see if you can remember all that we've learned today. An equilateral triangle has 3 symmetry lines. In an equilateral triangle, the symmetry lines are also medians, altitudes, angle bisectors, and perpendicular bisectors. The symmetry lines of the equilateral triangle intersect one another in the ratio of 2:1. I trust that you've enjoyed today's lesson. I hope to see you in Lesson 5, where we will be discussing points of concurrency of the lines that we have discovered while investigating triangles.